Right, this one might go slightly over 10 minutes because there's quite a lot to do. I suggest for this you do practice it, even if you're super confident, just pause the video a few times, do the mechanism, then check my answer against yours. So electrophilic addition is, of course, involving alkenes. I'll use propene every time as the example. That's not a display formula because I haven't expanded that to CH3, but all the important bits, i.e. the CC double bond, are present. We've got 3 different electrophiles to be aware of. Hydrogen halide, for example HBr, halogen, such as for example Br2, and sulfuric acid, which I'm going to write as such. If I've been teaching you, then you know about this already, but sulfuric acid structure is something you should know about, and it has that display formula. In concentrated sulfuric acid, that's what we've got. We've got like undissociated H2SO4 molecules like that. It's a very strong acid though, so given any opportunity, it'll give its H plus to things. That's an aside really. I'm not gonna draw 3 sets of arrows over that one structure there. I'll just do it for the first one. What we see every single time here is the double bond forms a bond with a H, or in the case of the halogen, one of the 2 BRs, obviously they're the same, so either, which causes the bond to break. Okay, that's the first step, and we could do the same thing for the others too. So I'm not going to do it, I said I wouldn't, but forms a bond, forms a bond. Now, let's see where that takes us. So I'm going to draw a really awkwardly long arrow, just so I can continue the mechanism with hydrogen bromide. Why don't you pause and finish it first before you have a look? And then I'm going to go through it for these next 2 as well. So if you want to get ahead, if you think it's worth doing, then draw those mechanisms as well. Anyway, so for propene plus hydrogen bromide, we have that first opening move, forms a bond from the double bond to the H, causing the diatomic to snap in half basically. HBr bond breaks. Now we've got this. Let me just do the template first. So the CC double bond has broken. We have a choice here about where it goes, so we're straight in this revision video talking about major minor products as well, which obviously I'll come back to and clarify a bit more. Now if the question, you'll have done either if you did pause it and go ahead, if the question asked us for the major products, then there's a decision to be made right here, which I'm going to talk about. Now this first arrow then represents the CC bonds double, like one of the 2 pairs within that double bond becoming a bonding pair with CH instead. 2 options. Either it goes on the end, and there we are, or, so we're going to talk about major minor here, it could go the other way around. In other words, it can go on the other, the hydrogen can go on the other of the 2 carbons. We've been asked for the major products, so by the end of this, we'll decide which one that should be. The carbon that doesn't gain the H has actually just lost the bond. In fact, it's lost an electron, because if you imagine that the double part of the second part of the double bond is a shared pair where each carbon puts an electron in, one carbon keeps both of the electrons in the CH bond that it now has. The other carbon that's left like without has lost an electron because it was in the double bond that's now CH bond on the other side. So it inherits a positive charge. There's always a negative ion at this point. That kicks off a bromide. When that bond breaks, the one bromine goes and the other gets attached. When that bond breaks, hydrogen goes as it's done here, and then you're left with the hydrogen sulfate ion, and I'm going to write that as OSO3H-. We'll do that one in a minute. So in this case then the bromide ion comes along, and just to finish the mechanism off, forms a bond with the C+. So this arrow must be coming from the lone pair on a Br-. If you forget the lone pair, if you draw the arrow going from the charge, if you forget the charge, there are each reasons to not get it right basically. So from the lone pair on bromide to the C+, and your arrows don't have to be excessively curly. There we are. As usual, there's no mark for the final product, but it gives us something to talk about. So we either get 2 bromopropane, CH3, CHBr, CH3, or we get 1 bromopropane over there where the Br ends up on a terminal carbon. And I'll write it backwards, CH3, CH2, CH2Br. Or if you prefer CH2Br, CH2, CH3, it's the same thing. Now, which one's the major product then? The major product comes about through the more stable carbocation intermediate. I'm not going to be writing notes on this on the sheet, you just need to listen and be reminded, hopefully, is what it is at this point. So this is a secondary carbocation. That there is a primary carbocation. How you classify it, it can go up to tertiary. It's simply the number of carbons attached to the C+, isn't it? This isn't the video where we go over all of this in detail, so just listen carefully if you need reminding. Basically, this is more stable than the primary carbocation alternative because there's a greater inductive effect. The adjacent methyl groups are sort of pushing electron density onto that C+, making it less positive, and that stabilises it. That just makes it more energetically favourable. This has got a lesser inductive effect. The ethyl group's pushing on less electron density than the two methyl groups are, effectively, and so this is stabilised less. So the more substituted your C+ is with carbon, the better, basically. So it wouldn't have come about in this mechanism because the structure wouldn't allow it, but the best case scenario basically is that we have a tertiary carbocation where whatever's attached to those, you've got like 3 carbons attached to C+. That would be a tertiary carbocation, that's the most stable type. The more stable are just literally more probable. Let's look at it like that. So this will be the major product. One of the most common mistakes, if you have to explain why it's the major product, people start saying, oh, well, 2-bromopropane is more stable than 1-bromopropane. That's a load of rubbish, okay? It's not to do with the stability of the products, it's to do with the relative stabilities of the intermediates that lead to those products. So 2-bromopropane is the major product because it is formed via a secondary carbocation, which is more stable than the primary carbocation, which is also possible in this reaction. And what I've done there for 2 marks usually is I've classified both carbocations as a primary and as a secondary, and then I've made the comparison. The secondary is more stable than the primary. That's how you get the marks there. Now, I'm going to skip BRBR and just do the alkyl hydrogen sulfate forming one, just so people have had a chance to see it. So if you wish to get ahead, we're going to do propene and conc sulfuric acid. Let's just say and sulfuric acid. It is concentrate. Here we go. Let's make quick work of this. So here's propene. Here is H2SO4 written in this style to make it look a lot like HBr. So the first opening move, an arrow from the double bond to the H. That H is delta plus because it's bonded to O. That's why it's attracted there. You don't have to show the partial charges though. Causing the HO bond to break, which is like that. Now, I'll do dodgy examples afterward. Let's just get this done. That gives us the intermediate. I'm going to go for the secondary carbocation, which would lead to the major product again, but you appreciate, because it's propane, there's a primary possibility, as we've just seen as well. So the double bond is now a single bond. That CH3 on the end is completely unaffected. I'll pop the H on carbon 1 so that the positive charge can be on carbon 2, and therefore it's the more stable secondary option, which, as we said, leads to the major product. Now, hydrogen sulfate is a negative ion. Conventionally, you can just put the negative charge in the top right corner and that's fine. Strictly speaking, it's on the O because that O has an extra electron. It got hydrogen's share of that bond back as well. So it's really the O on the end with the lone pair that has the negative charge, but you can stick to convention and put it in the top right corner and you're good. There's a lone pair on the O that has just lost H+, okay? So it has to be that lone pair going to the carbon. I'll give you some examples of how not to do it in a minute. And I will draw the product out. I'll even draw it out in display because you'll see it on some mark schemes when you're practicing. You will have already done that, I hope, by now. So now we've got that O that I formed the bond through connected to the sulfur, which has 2 double bond O's and an OH. And again, it's not display because of the methyl, but otherwise it would have been. So what we have here is now an alkyl hydrogen sulfate. And more specifically, this is propyl hydrogen sulfate, but more specifically still, it's on carbon 2. Not that you'll have to name this, but we could call that prop 2 yl or 2-propyl hydrogen sulfate. And hydrogen sulfate's usually written as one word, to be honest, but I'm going to have to put it over like that. I highly doubt you're going to have to name it. Let me just show you how not to do it then, or what could go wrong. So just for this intermediate step, I won't bother doing the first bit again. So let's just redraw the secondary carbocation intermediate, which was done perfectly. And just really, it's all about how, just try and avoid messing up drawing your OSO3H. If we wrote it as HSO4 minus, well, that is the formula for hydrogen sulfate, which is exactly what that thing is. But then we don't have a clear O to draw a lone pair on, and an arrow therefore coming from. So like that won't work. This would definitely not be acceptable. Okay, there is a lone pair on an O in a hydrogen sulfate molecule. The point is though, it's specifically the O was part of an OH group in sulfuric acid structure, which has just lost a H. It's definitely the O that we're talking about there. So this is no good. Okay, it really, that's why we use OSO3H, or yeah, that's why basically. So there it is. I think that's probably about everything there is to say. There's always a bit more we could be saying. Things to note here then, we're going from an alkene back to a haloalkane, or maybe a dihaloalkane. So like we got 1 bromo or 2 bromo, minor and major products coming off propene and HBr. If we had Br2, we'd add a Br and then another Br. So we'd have like 1,2 dibromo. Or we're adding this, oh, there's one more thing to say, the alkyl hydrogen sulfate. On a quick side note, and there's no mechanism for it, once you've got an alkyl hydrogen sulfate, I'm going to choose a different one now. So this is not the product we've just drawn. Now we've got ethyl hydrogen sulfate there. That would come from ethene and conch sulfuric acid. These can then undergo hydrolysis. Now, at best, a balanced equation is all we have to give. If you put that with water and warm it up gently, then no mechanism required. The hydrogen sulfate group falls off effectively and is replaced by an OH. So H2O is being split. The molecule is being broken down by the action of that. We'd end up with an alcohol. So from ethyl hydrogen sulfate, we'd end up with ethanol. And at that point, the OSO3H group takes one of the 2 H's from water. The OH that remains are now an alcohol, an OH group, and we went with that. So, and on to the next video where we talk about alcohol reactions across the whole process of ethene or any alkene, going with conch sulfuric acid to make an alkyl hydrogen sulfate. And then after that, that alkyl hydrogen sulfate being hydrolyzed, effectively what we get is the sulfuric acid showing a catalytic activity, because it gets used up here and replaced there. That gets formed and then used up. So in a single step, we're forming a final product, hydrogen sulfate, alkyl hydrogen sulfate, and the sulfuric acid has been consumed. But if we then consider what happens next to it, or what we might go and do, if we then add water, warm it gently, actually it then gets reused up, replacing the sulfuric acid, which tells us that across these 2 steps it's acted as a catalyst. And then we'd have alkene plus water makes alcohol, but not via the mechanism that I'm about to show you in the revision video I'm about to do, which is the direct hydration of an alkene, which doesn't follow anything like this. So there's, watch out for it. Okay, I better just finish that. C2H4 plus H2O in the company of sulfuric acid catalysts effectively gives us the alcohol. Right, thank you.